Logarithms, Lesson 3, Solving Exponential and Log Equations. This lesson isn't very long, but it is going to look at solving exponential equations using logarithms. In Lesson 1, we just used like bases. Here, there's going to be times when you can't get a like base. Now, with solving exponential and logarithmic equations, you are almost there. Just another couple of examples and strategies, and you will have mastered exponential and logarithmic functions. So far, you've solved exponential and logarithmic functions by equating exponents, using the same base property, exponentiating both sides, push up, condensing and expanding logarithms, and then factoring and using the zero product rule when you wind up with a quadratic. We have one last method, and that is taking the logarithm of each side. When is that necessary? When you have a problem such as this. 4 to the x is equal to 21. Well, in Lesson 1, we learned we look for like bases. Well, 4 can be 4 to the first or 2 squared. But 21 is a prime number, so I can't do like bases. Therefore, I can't use the like bases in setting exponents equal to one another. What I'll have to do here is I've got the original equation, and I'm going to have to take the log base 4 of each side. Well, when I do that, why is that helpful? Remember that log base 4 of 4 to the x asks, what exponent do I use with 4 to get 4 to the x? Well, that's just x. Remember that using a function and its inverse, logarithms and exponentials are inverses, gives you whatever your variable is. So essentially, the log base 4 with the base 4 raised to the x cancels those and drops down just to the x. Now, I have that equal to log base 4 of 21. I don't know exactly what that is, okay? I know it's going to be 2 point something because 4 squared is 16 and 4 cubed is 64. I don't know the exact value, but I can find it using a calculator, okay? So, here I can use the calculator or I can use the change of base formula. So we're going to do both of these in the video just to show you that they both work. Now, if you recall, we can go to math and then we can scroll all the way down to log base, and then we can put in the 4, and we want 21, and we get 2.196158711, on and on and on. It's an irrational number. It's approximately 2.196. Now, this is using a TI-84. What if you're stuck at home and all you have is a basic scientific calculator? Then remember, log of 21 divided by log of 4. The base stays the base, goes in the bottom, but we're going to use the natural log. So I can do log 21, don't forget your closing parenthesis, divided by log of 4. Now here, you can use the closing parenthesis or you don't have to. An ending parenthesis will be put on if nothing is there. I have to put it here, otherwise I'm going to do 21 divided by log 4 and then take the log of that. That's not what I wanted. 2.19615, same thing. So notice, the change of base formula is just what this guy is doing. This is just making us have to remember it. So either way, 2.196. Now, you can always plug it in here. And the thing that you got to be careful of is if I do 4 raised, and then I put 2.196, and I hit enter, I'm going to get 20.9953. Is that 21? No. Did I make a mistake? No. I rounded. When you rounded the 2.196, 158.711, on and on and on, you wound up with a rounding error. That rounding error shows up when you go to check. So you do have to be a little careful when you go to check. Now, what about this guy? Well, before you just run off and take the log base 3 of both sides, you have to get the exponential by itself. Because maybe in simplifying both sides, you'll wind up with something that you've got like bases, and you don't have to take the log base of both. So first thing I'm going to do is subtract 2 from both sides. And give me a pen back. And that will give me 4. Well, I can't 3, 4, 4 is 4 or 2. Can't do that. So therefore, I'm going to have to take the log base 3 of both sides. When I do that, notice log base 3 of 4 is a constant. It's a number. I don't know what the number is, but it's a number. And it's going to be 1 point something. Over here, again, remember that we took the log of 3 raised to something. So the log and the exponential are inverses of one another. So it simplifies, and I just bring down the 5x minus 2. Now I'm going to add 2 to both sides, and then I can divide both sides by 5. And oops, divide both sides by 5, and then I can get this approximation. So again, when you take your calculator, we're going to clear this. I'm going to have a parenthesis. It's got all of this. So it's going to be math, and I'm going to scroll down here just so that it looks exactly like what we have on the screen. Base 3 of 4. Okay, notice I'm going to come on the outside. So log base 3 of 4. Then I'm going to add the 2, close my parentheses. So I've got all of this divided by 5. And you get 0.65237, on and on and on. And again, if I plug just 0.652 in to check it, I will get close to 6, but it won't be exactly there. Next, there's a bunch of these for you to try. If you look at your notes page, you have 9 problems to try. What you want to do is pause the video, attempt these 9 problems. Some of them are exactly what we just went over. Others harken back to lesson 1 and lesson 2. So pause the video and try those. Are you back? Okay, we've got 1/3 and 2. I need to take the log of both sides. So I take the log base 1/3. How do I know what base it is? It's going to be this base, whatever the base is that's being raised to an exponent, so that using inverses they cancel. And I get my value. Now, over here, e raised to the 3 natural log of 2. There's nothing to do here but plug it into the calculator. Now, I can, and if you plugged into the calculator, you should get 8. If you do it by hand, however, oops, remember that this becomes e to the natural log of 2 cubed. Recall the properties of logarithms. Okay, then that means I have e to the natural log of 8. E raised to a power and the natural log, which is the log base e, those are inverses of one another, and so you're just left with the 8. This is one that you could solve no calculator. 3 raised to the negative x plus 2 equals 18. While 3 will go into 18 evenly, I cannot do 3 raised to a power, a nice even power. So for this one, I will need to take the log base 3 of both sides. When I do that, the log base 3 of 3 raised to something will leave me just with the exponent. Over here, I've got this crazy constant. I subtract 2 from both sides, and then I'm going to divide both sides by -1, or subtract or multiply by -1, either one. And then I'm going to plug this expression. And don't forget, you will need to put your parentheses around this when you put it in your calculator. And I will come up with, oh, there we go, sorry, with -0.631. Over here, I need to solve for x. Remember that e is irrational, so I can't take this irrational number to some power and get 40. So what I'm going to have to do is take the natural log of both sides. Log base e is the natural log. Now, natural log and e raised to a power cancels, and I get 2x plus 3 is equal to the natural log of 40. Subtract 3, divide by 2 or multiply by a half. It's the same thing. And then plug it into the calculator. Beware here. While 5 will go into 10 evenly, I can't write these two as one as an exponent of the other. Okay, whoops, sorry. So what I have to do here is I'm going to need log of 10 raised to the x is equal to log. Why did I not put log of 5? Why didn't I put a 10 here? Because log without a subscript is log base 10. That's our common log. Cancels this out. X is simply equal to log of 5. And when I get my calculator up, I simply hit log 5, and I get 0.6989. So 0.699. X is approximately equal to 0.699. Whenever you've got a decimal, whenever you've got 0 point something, it's a good idea to put 0 point so that somebody doesn't miss this decimal point when they're looking at your answer. Big difference between 699 and 0.699. Okay, over here, first thing I'm going to do, divide both sides by 2. E to the point 0.34 t, which is going to go like this and come back. So if you're looking at this, just still, okay, 50 divided by 2 is 25. Take the natural log of both sides. So if I do the natural log here and the natural log here, I'm going to have 0.34t is equal to the natural log of 25. Dividing both sides by 0.34, t is equal to the natural log of 25 divided by 0.34. Plugging that into the calculator, well, look at that. This is what I should get. Didn't even know that. How's that look? Just pull all this right up here. I must not have erased that from a previous time. But I'll go through the calculator because sometimes some people push the wrong buttons or don't put parentheses in the right spaces. So we have the natural log of 25, very important, close that parenthesis, divided by 0.34. Hit enter, and there's your 9, 4, 6, 7, 2, 8, on and on and on. Okay? Now, this next one, this is an exponential. Notice e to the 2x minus 2e to the x. This could be e to the x squared. So I have a quadratic. I have something that's written in quadratic form. So therefore, I can rewrite it like this. So it's a little bit easier to see. I've got e to the x squared minus 2e to the x minus 15. Now I factor that. E to the x minus 5, e to the x plus 3. E to the x is 5, e to the x equals negative 3. If I take the natural log of both sides, what will happen here? I'm going to get an error. Remember that e is a positive number. There's no exponent that I can raise e to and get a negative value. So this side won't work. Only this side will work. So now, oops, I'll just put this over here. Notice natural log of 5 is 1.609. This is my answer. This is an error because there is no way to raise e to a power and get negative 3. Okay, over here, 3 to the x equals 1/9. You do not need to take the log base 3 of both sides. Remember that I can rewrite 1/9 as 3 to the negative 2, which very quickly tells me that x is negative 2. Be careful you don't just jump to the hardest problems. Recall your easy problems. Oh, natural log of e. This helps if you think about it as log base e of e. These cancel, right? So you just have 1. Because remember, the exponent here is 1. So your answer is 1. Excellent job. Now, why, oh why am I torturing you with logs and exponentials, particularly logs, because these are these crazy things. And by the way, logarithms are not trig. Just because it's a word does not mean it's trig. Where will you ever use these beastly things? Well, music uses logs. Geologists, seismologists, climatologists, and astronomers use logs. Scientists use it. Prehistorians, investors, and financial people, bankers, use it, and many other jobs. Logs are found in pH scales. Those are logarithmic. Incredibly large timelines, incredibly large distances when you start talking about space. Decibel scales, loudness of music, loudness of sounds, decibel scales, those are logarithmic. The Richter scale, which measures earthquakes, the intensity of earthquakes, that's a logarithmic scale. Cryptography, a lot of cryptography uses logs. Anything involving growth or decay rates, from investment accounts to petri dishes to radioactive materials, all use logarithms. Asking why we use logarithms is like asking why would we use a square root or exponents. Logarithms describe certain relationships between values and allow us the ability to find those values. The force is strong with you, and I know that you too are now a master of logs.